The chain rule gives the derivative of a composition of functions. A composition is where you take a function, say g of x, and then you take its output and put it into another function, say f of x. So our composition of functions here, h of x, is given by f of g of x. And the chain rule states that the derivative of this composition is going to be the derivative of our outer function, f of gx, with respect to gx, and then you multiply that by the derivative of g with respect to x. And when you use it enough times and you get enough experience, this is one of those things you apply without even thinking or even realizing you're doing it. But the first time you come across this formula looks a little bit strange. And there's another way of writing this using Newton's notation, which I've put here on the screen. And this looks a little bit more like you could derive it. You can see that, for example, the du's cancel and you end up with dy by dx. But if I showed this to you for the first time and said, how do you feel u and y and x are related in this? Because of that multiplication, you might be tempted to think this is a derivative of the product of two things. So what I want to do in this video is to get a nice visual understanding of why the chain rule requires us to multiply the different functions together. I will say the reason it's called the chain rule is because you can compose as many functions as you like. You can then make a long chain of derivatives until you reach the limits of your sanity. So what are we trying to do in this video? We're trying to understand where these two terms, these two things you're multiplying together in the chain rule come from. Firstly, on the right, what does it mean to take the derivative of a function with respect to another function? And then on the left, why do we have to multiply our derivative by this second derivative? And I'll just say this video is aimed at people who have just come across the chain rule. And it's not a formal proof of the chain rule that we're aiming for. It's more gaining a visual understanding of where these two parts come from. And to illustrate this, we're going to build up to differentiating the function y equals sine x squared. And the prior knowledge that I'm assuming you have is that you understand what a gradient is, how you calculate it, and why you might want to. Also, I'm assuming that you can differentiate simple functions such as ax to the power of n, where a and n are integers. And finally, I chose to use a periodic function, sine, because I think that will be easier to visualize. If you haven't come across this yet, the derivative of sine of x is in fact cosine of x. And I'll leave that to you to think about if you've not seen that before. But otherwise, let's get going. Before we get started, I always think it's useful to give a nice physics example of where we could use the chain rule. In fact, there are lots of different examples, but one that particularly resonates with me at the moment because I'm currently in Tokyo and I came here from London with my wife and her violin. And of the three of us, I think it's fair to say the violin did the worst out of the journey. And the reason for this is because, of course, the fundamental frequency of the strings on the violin is a function of the tension in the string. But again, the tension in the string, that depends on the humidity of the air that the violin's in. And the humidity here in Tokyo is rather different than the violin's used to in London. And so if I wanted to try and calculate how the change in humidity has changed the frequency of the strings, well, the frequency is now a composition of the tension, which depends on the humidity. So in order to analyse this, I would need to use the chain rule to differentiate it. Although I would suggest that a more useful thing to do would be to find a good luthier to get the violin back into shape. But while you're waiting for the luthier, you can use the chain rule to work out what's going on. Okay, Before we move on to looking at the chain rule properly, let's do a warm-up exercise. What we're going to look at is the function fx equals sine of x, and we're going to multiply everything by 2 to get 2 times sine of x. And we're going to see how that affects the gradient of the graph. And in order to do this, I'm going to go on to the super useful online graphical calculator from Desmos. The red line here gives us the graph y equals sine x. And the blue dashed line is the derivative, which is cosine of x. And if you like, you can take a second to check that when the gradient of a sine x is a maximum, the derivative, the blue dotted line, is also a maximum. And what we want to do is we want to change the value of a to see what happens to our y equals sine x graph as we go from y equals sine x to y equals 2 sine x. So let's do that, scaling, and you see that if we double y equals sine x, the red line ends up twice as big. So we're going to twice as high a value. We're going up to 2 as a maximum here. And now we need to think about what that's done to the gradient. You'll notice that the gradient is now steeper around, for example, x equals 0. And our y equals cosine x, the derivative graph, hasn't reflected that. And I will say that because the graph is going up to twice as high a value for sine x, it means that the gradient is twice as large. Y equals 2 sine x is twice as steep as y equals sine x. So to mirror that, I'm just going to multiply my cosine graph by 2, and now this blue dashed line shows the derivative of the y equals 2 sine x curve. So let's recap what we saw there. We took the graph y equals sine x, we scaled it, we multiplied by 2 to get y equals 2 sine x, and that caused the gradient to change. Because we were multiplying the function by 2, we caused the change in y to double. And as we cause the change in y to double, if you follow through the gradient formula, you see that the gradient at each point is double what it was before. In other words, the derivative of y equals 2 sine x is twice that of the y equals sine x. And that's summarised there. Now, this isn't the chain rule. We haven't reached the chain rule yet, but this is something useful to bear in mind when we start changing the function in the brackets, when we start changing the x in the y equals sine x around. Having looked at what happens to the derivative when you scale the output of a function, we're now going to look at what happens when you scale the input of the function by an integer. So to do this, I'm going to compare y equals sine x with y equals sine of 2x. And the first thing I'm going to do is I'm going to plot the function versus its input. In other words, sine of 2x versus 2x. And when I do this, we find the graph once again looks exactly like y equals sine x. I've scaled both the x and the y axes, so we have a graph of y equals sine x again. So if I'm going to differentiate this, then so far the derivative looks exactly the same. So the derivative of the y equals sine x graph is y equals cosine of x. So I'm going to make a guess, hazard a guess here, that the derivative of the y equals sine 2x is going to be cosine of 2x. And I'm going to plot this on Desmos in a second, and we'll see that this does give the correct gradient to within a scaling factor. So we're almost there, but we've ignored the fact that the x-axis has been squashed. When I scale x up by some value, it's a here, as I move from a equals 1 to a equals 2, the graph gets squashed in the x direction, like that. There it is. And the reason for that is because our function, instead of returning the value of sine for x, it's returning the value of sine for twice x, and that leads to that squashing. And if I turn on the graph of y equals cosine of 2x, we can see that when the y equals cosine of 2x graph reaches 1, that's indicating the maximum gradient of the y equals sine 2x graph, which is good. We can see that to a certain degree we've succeeded in finding the derivative of y equals cosine of 2x, but it's not quite right. The reason it's not quite right is to do with the fact we've squashed the x-axis by a factor of 2. So comparing the graph of y equals sine x with y equals sine 2 of x, we see that it's very similar, it's just been squashed in the x direction. The x direction has been halved. And so when we take our gradient, we're doing our change in y divided by change in x, and that denominator has now been halved. Now when you divide something by a half, you double your outcome. So what's happened here is the gradient has been doubled. So if we differentiate y equals sine x to get the cosine of x, differentiating y equals sine of 2x gives twice the cosine of 2x, because squashing the x-axis doubles the gradient. And just to confirm, here is the graph of y equals sine 2x in red, and the graph of y equals 2 cosine of 2x in the blue dashed line, and we see that the gradient is now correct. When the sine x graph goes through the origin, the gradient is 2, and that's reflected in the blue dashed graph. So we're now a step closer to understanding the chain rule. To summarise, we take the derivative of the outer function, so fx, I'm calling it here, with respect to the function that's used as the input, gx, and then we have to multiply this by a scaling factor. And so the final question is, what is that scaling factor, and how does it depend on our function gx? Now we're going to differentiate y equals sine x squared, which was the original aim of this video, and use that to illustrate how the chain rule works. As we've seen, we can simply imagine that x squared is a variable on its own and differentiate with respect to x squared. So the derivative with respect to x squared of sine x squared is just going to be cosine x squared. But to get the derivative of this function with respect to x rather than x squared, we need to multiply by a scaling factor. And the question is going to be, how does the scaling factor depend on x squared? And it's not going to be as straightforward as the previous situation. To illustrate this, in purple I have the graph of y equals sine x squared, and the red dotted line is y equals sine x. And we can see that the scaling now depends on x. As x gets larger, the sine curve is getting more squashed in the x direction. So we need to find out how our scaling factor depends on x. To see how we scale the graph, let's plot the graph of y equals x squared, and let's pick a particular value of x. I'll just randomly pick this point here. And to find the scaling factor for this point, all we do is we take a little region around there and take it up to the line of the graph. There we go. And then we're going to see how y changes, or how x squared changes, as we change our value of x. So let's trace across the y-axis. That's nice. And then we're going to look at how this change in x here causes a change in y over there, or in x squared on the y-axis. And by now, I think you realise that when I'm talking about this scaling factor, all I mean is the gradient or the derivative of my function y equals x squared. So it turns out that scaling factor is simply the derivative of our function gx, which is inside of our larger composite function. So now we know that this scaling factor is simply the derivative of, in this case, x squared with respect to x, and the derivative of x squared with respect to x is 2x. And so we now have our full derivative of y equals the sine of x squared, and that's 2x multiplied by the cosine of x squared, where the cosine of x squared we found by differentiating sine of x squared with respect to x squared, and then we have that correction scaling factor 2x, which is the derivative of x squared with respect to x. And to show you that this does work, I've plotted separately here the graphs of y equals sine x squared at the top, and underneath is the graph of y equals 2x cos x squared, and you should see that the gradient of the top graph is equal to the y value of the lower graph. So that's where those two parts of the chain rule come from. Firstly, you have on the right the derivative of your function, the outer function of the two, with respect to the outcome of the first function, which I called gx. Then, because gx squashes or stretches the graph along the x-axis, we have a correction factor, which is just the derivative of gx with respect to x. And now to finish, I'd like to leave you with a little exercise, and it's to do with the symmetry of the various functions we've been looking at. You may have noticed that some functions, such as the sine of x and 2x multiplied by the cosine of x squared, have a sort of rotational symmetry around the origin. If you rotate each of those graphs by 180 degrees around the origin, you end up with the same graph. Whereas some of the graphs we've been looking at have been reflected in the y-axis. For example, look at the cosine of x on the right there and the sine of x squared. These have a reflective symmetry. And we have a name for these two different types of functions. The ones on the left are called odd functions, and the ones on the right are called even functions. And you may have noticed that when we differentiate the odd function, like sine x, we end up with an even function, cosine x. And when we differentiated an even function, sine x squared, we ended up with an odd function, 2x cosine of x squared. And the exercise is to use the chain rule to show this fact. So here I have a little mathematical statement of what an odd function is and what an even function is. Can you use the chain rule to show that when you differentiate an odd function, you end up with an even function, and when you differentiate an even function, you get an odd function? And is there any function which doesn't follow this? Are there any dark horses out there? That's all. I hope that you've found this video useful. It's been a pleasure making this, and thank you for watching.